Hello, AP Stats. So I realized that I thought it was important to go through a couple of activities that we are not going to do in class because this is what you were doing over the break. But as I was looking, I realized there were some things here that I thought might make more sense if you had a video to watch back of going through some of these activities together and kind of seeing how to use the T-table and also how to use the calculator for a few of these. So that's what we're going to do here. So we're going to look at, are you getting enough sleep? So it's recommended that teenagers get 8 hours of sleep a night. Mrs. Gallus believes her AP Stat students are getting less than the recommended 8 hours of sleep per night. To test her belief, take a random sample of 10 students in class and record the number of hours of sleep for each. Do these data provide convincing evidence that the AP Stat students get less than 8 hours of sleep per night using alpha of equal to 0.05? So let's say I have some data for us. Our sample data here, I'm going to give to us here is 6.5 hours, 4.75, 5 hours, 8 hours, 7 hours, 7.25 hours, 4.5 hours, 5.5 hours, 7 hours, and 6 hours. So let's take a moment to, we're going to take a moment and remind ourselves in the calculator how to calculate the mean and the standard deviation. So in my calculator, I'm going to go to Stat, Edit. I'm going to clear out what's in there and I'm going to enter this data. So 6.5, 4.75, 5, 8, 7, 7.25, 4.5, 7, and 6. So I've entered in all of the data. I'll go back to Stat, over to Calculate, and I'm going to use that one variable statistics. I did put my list into L1. So coming down to Calculate here, I get a mean of 6.15. And a standard deviation, a standard error rather, because this isn't a population, a standard error of 1.185 or 1.19. So my mean is 6.15 hours and my standard deviation is 1.19 hours, or my standard error. So let's state the appropriate hypotheses for the significance test and make sure we define the parameter of interest. When it's asking for the parameter of interest, I've noticed this in some of our CFUs, don't just say the true mean of, but we have to state what the symbol is. So here we're going to say mu equals. Without that, we're not actually defining the parameter. So mu equals the true mean hours of sleep for Mrs. G's AP Stats students. And then this also asks us to state the appropriate hypotheses. So I've got my null hypothesis. Remember, the null hypothesis is always the parameter equals something. And so up here, we see that we're looking for convincing evidence that the AP Stats students get less than 8 hours of sleep per night. That right there is giving us also, that 8 hours is giving us also our null hypothesis. So our null hypothesis is going to be mu equals 8 hours. And our alternative hypothesis, the mu is less than 8 hours. Next, we have to check our conditions. So which ones must be met? We've got the same conditions as always. We've got our random. Well, we did take a random sample of 10 students. So that one checks. We've got our 10% condition. We're going to say that it is very likely that 10 is not less than 1/10 of all of Mrs. G's AP Stat students. So this one does not pass. And next we have to check normal. Now for normal, it does not tell us in our description that this is normally distributed, that the population is normally distributed. It also does not, we also do not pass the central limit theorems. We do not have more than 30 in our sample. So the other option is to sketch out our distribution here. So we have 4 hours, 5 hours, 6 hours, 7 hours, and 8 hours. And we're going to make sure that our sample data is not strongly skewed and doesn't have any outliers. So we'll just fill this in. So 6.5, 4.75, 5, 8, 7, 7.25, 4.5, 5.5, 7, and 6. So there's no strong skew. And there aren't any outliers when I look at our distribution of the sample data here. So the sample shows no strong skew or outliers, which means that our sampling distribution is approximately normal. So normal is going to check. Now we didn't pass the 10% condition. So we're going to add in what we would state here in our free response question to continue. So we must be cautious of our results because the 10% condition was not satisfied. So this is that whole, we're going to proceed with caution, but we're going to be cautious with our results. You would want to add that. Chances are you won't get something that will have a free response question that will have something not be satisfied, one of the conditions not be satisfied. But if you do, write something like this, and we want to specify which condition was not satisfied. All right, so then giving our formulas for the mean and standard deviation of the sampling distribution of X bar, and then we're going to calculate those values. So we know that the mean of the sampling distribution of the sample mean is equal to the population mean. And for our, when we're working with the mean, we're going to assume that that is our null hypothesis here. So that we are going to assume is 8 hours. So this is from our null hypothesis. And then the standard deviation of the sampling distribution of the sample means is equal to the population standard deviation divided by the square root of n. But we don't know what the population standard deviation is. If we knew this, we would know what the mean is for sure. So instead, we're going to use, this is going to be approximately equal to the standard error divided by the square root of n, which is 1.19 divided by the square root of 10. And if you do that calculation, that's 0.376. So because we are not using the standard deviation, we're using the standard error, we are going to use the t distribution, which is what's new here. Okay, and the reason again for that is because we are using this the standard error, not the standard deviation. So the picture is going to look very, very similar. Still going to look very similar to our sample or our normal distribution here, but we're going to label this as our t distribution with the degrees of freedom. So our degrees of freedom are n minus 1, which was 10 minus 1. Our degrees of freedom is 9. So we're going to label this as T9. Our 8 is in the middle here, and then our 6.15, which was our mean, our sample mean is somewhere over here, and we're looking for that probability of less than. The next thing we need to do now is find, instead of our z-score, we're going to find our t-score. So this is going to be very similar to finding our z-score, but it's the t since it's the t distribution. So it's still going to be our sample mean minus the true mean that we're assuming, divided by that standard deviation of the sample mean, of the sampling distribution of the sample means that we found, which was 6.15 minus 8 divided by 0.376, which was negative 4.92. Okay, so this 4.92 right here is what I want you to remember. Because now, using this test statistic, right, that negative 4.92 is our test statistic, we're going to come down here to number 6. Since we're working with means, the test statistic is a t-value. So we're going to use that t distribution, table B, to find the p-value. So the first thing we're going to do is look for the row that we're looking at. Our degrees of freedom was 9. The second thing we're going to do is we're going to go across to find as close as we can to the 4.92. And then that third step is to match the tail probability at the top. So I'll show you that here on our table. So I'm going to go to our formula sheet and tables, coming down to, this will be page, this will be table B here. Okay, so we don't care that it's going to be the positive tail probability. We care that it's going to be, so what we're going to do is we're going to come and find our degrees of freedom. Here I see the 9. So I'm looking for degrees of freedom at 9, and then I'm going to come across until I find as close as possible to that 4.92. We notice that that's at the very end. 4.781 is as close as we can get. And if we come up from there, that tail probability is 0.0005. Okay, 0.0005. So my p-value is 0.0005. Showing that again, find your degrees of freedom on the left. Come across to as close to the test statistic, your t-value, as possible. So that was, we had 4.92. So here I have 4.781. That's as close as I can get to that. We have to keep the same degrees of freedom. And then coming up, 0.0005 is the closest tail probability. That is how we use table B to find the p-value if we need to. So what conclusion can we make? Well, because 0.0005 is less than our alpha of 0.05, we reject the null hypothesis. And have convincing evidence that Mrs. G's AP Stat students have a mean hours of sleep less than 8 hours. We slip this down just a little bit so we can see all of that put together. We've kind of done our state plan do conclude, minus naming this test. If we come back up here just to add that name in, we would have put it right around this condition, these conditions. This would be a 1 sample t-test for mu. There we go. We've got actually the entire process here now, just not labeled as we might label it on a free response question. This would be a great place to pause and go back. We're going to do one more activity in this video, and then you can go to Canvas to find copies of the notes. In the next part of the video, in the next activity, we're going to look at how we can do some of these calculations using the calculator as well, because some of this we can do in the calculator, which is especially helpful when we're looking at multiple choice questions. So secondly here, we are going to look at normal body temperature. So for many years, we've been told from doctors that normal body temperature is 98.6 degrees Fahrenheit. And so if we took our body temperatures, let's say we had a class of 32 students and we all took our body temperature, and the average was 98.237 degrees Fahrenheit. And our standard deviation was 0.822, our standard error of that sample. Do the data provide convincing evidence that the mean normal body temperature is different than the doctor's claim? Couple of things here. Do the data provide convincing evidence? Right here. This should be an immediate clue to us that we need to do a state plan do conclude. Additionally, within this, I see the word mean, which means I know I'm going to do something with T, with a T distribution, and different, right? So that's going to be a not equal to here. Okay. Additionally, as I continue reading, assume the conditions have been met, which means we don't actually have to check these, which is really nice for us. So we're going to do a T test here to test this doctor's claim. So our parameter mu equals the true mean body temperature for all high school students. Our statistic then, if our parameter was mu, our statistic should be X bar, and we already know that that is 98.237. Our hypotheses, our null hypothesis is always an equal to, and we're assuming that the doctors are telling us the correct information, that mu is actually 98.6 degrees Fahrenheit. And since we're looking for convincing information that it's just different, then our alternative hypothesis is going to be that mu is not equal to 98.6. And this is what makes this two-tailed, okay? Because it's not equal to, we're going to have a two-tailed test here, which we'll talk about what we need to do when we get down to the do. And let's just set our alpha value at 0.05, okay? Naming our procedure here, it's the same name, even though it's two-tailed, it's still the same name because we still have one sample of 32 students. We're looking for the mean, so it's going to be a t-test for the population mean. So we know that when we're doing this test here, and then the conditions, we would also usually check conditions here, but since it told us to assume they've been met, we don't need to check any. So the general formula is where we're going to do our test statistic, right? So that's going to be our T equals X bar minus mu divided by the standard error divided by the square root of n, since we haven't actually calculated this yet, right? We haven't calculated the standard deviation of the sampling distribution. So we're going to calculate that here. So then I work T equals the sample mean I'm working with 98.237 minus my assumed population mean of 98.6 divided by, I need to fill this part in, my sample standard deviation was 0.822 divided by the square root of 32. If I were to do this in my calculator, this one is a little bit more complicated because I do have that square root on the bottom here. So what I would do is do my subtraction first. Okay. And then divide that by, notice it just pulls an answer, parentheses, 0.822 divided by second square root of 32 to get negative 2.498 or negative 2.50. So my test statistic T is negative 2.50. So now let's sketch out our T distribution. Okay, so we know that this is going to need degrees of freedom, which is n minus 1. Our n was 32, so our degrees of freedom was 31. So this is a T distribution with degrees of freedom 31. Because we know this test statistic, we can put 0 in the middle. So that's like the standardized middle, right? The standardized mean. We have the negative 2.50 on the left. And we're looking for outside of that, but this was a two-tailed, right? Because it was just not equal to, so we'll put the positive 2.50 on the right. And now let's go find that p-value. So I'm going to look for 31 as my degrees of freedom. If we don't see it, remember we always round down. We always round down. So we're going to go to the 31. Yes. Let's see here. We don't actually have 31. We have 30. So instead, we're going to go with 30 and because we want to stay less than, and then we're going to get to as close as 2.5 as we can. 2.457 is as close as we've got. So then we'll go back straight up from there and we have 0.01 as our p-value. So one tail has a p-value of 0.01, right? So this one tail has a p-value of 0.01, but I need both of those tails. So I'm going to multiply that by 2. So my p-value for this two-tailed is 0.02. To conclude here, because 0.02, let's see, that's less than our 0.05, less than the alpha equal to 0.05. Because it's less than, we reject the null hypothesis. And we do have convincing evidence that the mean normal body temperature is different than the doctor's claim. I want you to notice something here. So we rejected the null hypothesis. And then this whole part here that we said we do have convincing evidence that the mean normal body temperature is different than the doctor's claim. I literally just rewrote that from what it was asking. Do the data provide convincing evidence of this? Yes, they do. I just repeated it. Nice and simple. So we just did the state plan do conclude. Now let's take a look at what this looks like in the calculator. Okay, so another class did the same activity, but they got different results. So we're going to use these results in the calculator, not the ones we just found. Using t-test on the calculator, I'll show you where it is. We'll find the p-value for this test or for this sample, okay? So move this to where you can see it. Your tests are under stat, and you're going to come all the way over here to tests. And look, right here, we've got t-test. So we're going to come down and press enter. We're going to enter the statistics, okay? So usually we'll have stats to enter here. So we are going to assume that our mean was, that's the mean for the hypothesis, so 98.6. Our sample mean was 97.9. Our sample standard deviation was 1.6, and our sample size is 30. Here we are looking for a different than, not a less than, not a greater than, but a different than. So we'll come down and calculate. And right here, we see we have a p-value of 0.023. Okay, so our p-value right here is 0.023. You also notice we've got our t-score of negative 0.2396 or negative 0.240. So our p-value was 0.023. So let's think, would we reject the null hypothesis at an alpha of 0.10? Well, 0.023 is less than 0.100. So yes, we would. Would we reject it at 0.05? Well, yes, it's still less than our 0.05. So yes, we would. Would we reject that at 0.01? No, we would not, because 0.023 is greater than 0.01. So we would not reject it at 0.01. So let's also take a look at the t interval on the calculator, because guess what? Our calculator can also calculate confidence intervals for us. That is also going to be under stat tests. And we're going to come down here to number 8, to t interval. We're still going to input stats. Notice it pulled it right over for us. So 97.9, 1.6, 30. And then our C level, it wants that percent as a decimal. We're going to start with a 90%. So we'll put 0.90, which it'll change to 0.9. That's fine. Calculate it. Give it a moment. There's that first interval. So let's write that down. 97.404 to 98.396. Would we reject the null hypothesis for this? Well, remember our null hypothesis was that mu equals 98.6. Does this contain 98.6 or does it capture 98.6? No, it does not. So we would reject the null hypothesis. We could do that again. So stat, tests, t interval. We have the same statistics, and let's change it to a 95% C level, 0.95. So we have 97.303 to 98.497. Does this capture our null hypothesis? No, it does not. So we would reject the null hypothesis again. Let's do one more at the 99% confidence level. So changing that to 0.99 this time. This one is 97.095 to 98.705. Does this capture 98.6? Yes, it does. So we would not reject the null hypothesis. One thing I want you to notice here is that the alpha level and the percents, the alpha level here was 1 minus that confidence level. So for an alpha of 0.1, 90% was our confidence level. We rejected both times. The only one we didn't was when we had an alpha level of 0.01, which was a 99% confidence interval. We did not reject those. So here, what connection do you notice between your answers to number 1 and number 2? The decision to reject or not reject is the same regardless of using a confidence interval or a two-sided significance test. One thing that you'll also see in the notes when you open up that PDF, in order for this to work, the confidence interval and that two-sided significance test, it has to be two-sided. It cannot be a one-sided significance test. If you need to go back to watch how we did both of those in the calculator again, you can do that. Additionally, let's real quick here, just go back up to our original information and let's go through how to do that significance test, the t-test in the calculator. So again, I'm going to go to stat, over to tests, t-test. I'm going to input my statistics. So still 98.6. Now let's use this 98.237. The standard deviation of 0.822. Our N was 32, and we're still not equal to, right? Because it was still different. So our null hypothesis was still a not equal to. Calculate. We have a slightly different p-value, all right, slightly smaller, but remember that we didn't actually have a degrees of freedom of 31 on the table. We got the same negative 2.498 or negative 2.50 as our t statistic. We still would reject the null hypothesis at the 0.05. That is one way we can use this.